All right, so let's consider another method for solving differential equations, partial differential equations. This is the Rayleigh-Ritz method. So let's consider the following PDE, right? So nabla squared u is equal to f in the domain, and u is equal to 0 on the boundary. Okay, so you fix omega, and you consider an inner product space. Let's call it V, right, whose functions you have the property that uxx and uyy are continuous. In omega, and uxy equals to 0 on the boundary. Okay. Then you also assume that f is continuous. In omega. So with that, you should expect to find that the solution u is contained in V. So the solution u, right, should be in V. Okay, and then the inner product we use is the L2 inner product, right? So the inner product is the L2 inner product. Okay, which is that uv is equal to the integral over the domain of uxy vxy dx dy. So you can think of this as being a little bit like the infinite dimensional generalization of the dot product between two vectors, where now u and v can be thought of as infinite dimensional vectors, if you will, indexed over sort of the domain omega, right? And so you take this pointwise thing, and then you sort of, instead of doing the sum, it's like you integrate over the domain, right? So that's sort of a natural analog, if you will, of the dot product, if you squinted it for a bit. Okay. So in any case, it's like what we're going to do is that with this inner product, we're going to rewrite these equations. It's like using this inner product. And in order to do that, it's like we're going to have to say something about properties of the Laplace operator with respect to this inner product. So let me state the theorem, and then we'll prove it. Okay. So the theorem is as follows, right? That the operator negative nabla squared is self-adjoint. And I'll explain what all these mean. And positive definite. On the inner product space. V. Okay. All right. So let's see what exactly this means. Let's prove this theorem. Okay. So the proof is as follows. So, all right. So the property of being self-adjoint, or otherwise referred to as symmetric, right? Is the following, that, okay, so if you take this operator, negative nabla squared u, acting on v and you pair it with, so negative nabla squared u, it's, sorry, negative nabla squared acting on u, and you take the inner product of that with v, right? That's equal to u paired with that operator acting on v instead, okay? Okay. If you want to think about this in the context of matrices, so a sort of remark, right, in the context of matrices, right, what you have is the following, right? So you have an inner product between, say, m u with v, which is equal to mu, so that's a vector, right? So if u is a vector and m is a matrix, m times u is a vector, transpose v, right? So, so the vector, it's like paired with another vector via the dot product, can be expressed in terms of the transpose of the first vector multiplied by the second vector, at least if the vectors are viewed as column vectors. Okay, so you have that on the one hand, and then you also want that u is u paired with mv, right? So you want this equality, but this is equal to the following. So that is equal to u transpose mv, but this is u transpose m transpose v, right? So if this is true for any u and v, then that basically is saying that m is equal to m transpose, which is our usual notion for a matrix being symmetric, right? So anyway, so the point, if you will, is that this notion of self-adjointness of the operator, or the operator being symmetric, is a generalization of the thing you've seen before for matrices being symmetric, okay? All right, anyhow, okay, so let's go back to this thing here. So to prove this equality, so to prove that negative nabla squared is symmetric, right, you can use Green's theorem together with the condition that, you know, it's like you have these trivial boundary conditions, right? Use Green's theorem plus vanishing boundary conditions. Because if you recall, all the functions that's like in this inner product space V vanish on the boundary, right? Okay. So, and then let me just remind you what Green's theorem says. So Green's theorem sort of states that the integral over a domain of px plus qy dx dy is equal to the integral over the boundary of p dx minus q, sorry, p dy minus q dx. Okay, all right, so let's see how you can use this to prove that the Laplacian is, negative Laplacian is symmetric. I guess for symmetry it doesn't really matter whether it's plus or minus. Okay, so anyway, so let's look at this left-hand side. So nabla squared u v is equal to the integral over omega of uxx plus uyy multiplied into v dx dy, right? That's just the definition given the L2 inner product that's like of these two functions. Okay, so I'm going to write this into a form, it's like which allows me to apply Green's theorem. So this is the integral over omega of uxx, sorry, ux vx plus uy vy. Okay, but that's not quite right, right? Because I have to subtract off some terms, minus let's see, ux vx minus uy vy. Right? Because if I differentiate respect to x, it's like the product rule says I get uxxv, which is sort of what we had before, but we also have a ux vx term, which I have to subtract off. Okay, so that's basically what I'm doing here. All right, dx dy. Okay. Okay, so this is equal to the integral, well, the integral, a one-dimensional integral over the boundary, right? Because this is just a two-dimensional domain of uxv dy minus uyv dx. Okay, all right, so this is the part which so this piece is what I apply the Green's theorem to, right? So this integral becomes something which is an integral over the boundary. This piece here I'm just going to leave in terms of sort of an area integral minus the integral over omega of ux vx minus uy vy dx dy. Okay? Right. Okay, and then this term here, right, vanishes because u and v vanish on the boundary, right? So this has to vanish. So you just have that, okay, and you can do the same thing with the other part. So similar calculations gives you that u now plus v, right, is equal to this. Vxx plus vyy, sort of u dx dy. So basically the only thing I've done is to change, I mean, it's like you can see that equation, it's like just involves swapping u and v's, right? So so a similar calculation gives you that this is equal to negative of that, but every time you see a u, I replace it with a v. So this comes v x u y minus vy, sorry, vx ux vy uy dx dy, but that's equal to this, right? So this is equal to nabla squared uv. So that means that nabla squared is self-adjoint or symmetric. Okay. All right. So again, it's like you used Green's theorem, and you used the fact that the solution bound, the function u, it's like nv, it's like vanishes, it's like on the boundary of the domain. So if the domain actually was just a rectangular domain, it's like in R2, then you could have just applied the usual integration by parts. It's like twice for each of the pieces and gotten the same result. But omega here is not, it's just some domain in R2, it's like which is sort of nice enough, right? And so then in that more general case, you have to evoke Green's theorem. So that's one piece that, you know, nabla squared is self-adjoint or symmetric. So we want to show, that it is positive definite as well. Well, negative nabla squared is positive definite. Okay. So what that means is that, so in order to say that this operator is positive definite, you have to show that, so need to show that for u in this inner product space V and u not zero, that negative nabla squared u paired with u is greater than 0. Okay. And then the previous calculation we had before allows us to show that this is equal to the integral over the domain of ux squared plus uy squared. Sorry. Yeah. So that's just a sum, and I might have messed up the sign, but it's just yeah. So these two, it's like I just added together, and there's a minus sign here, and so if you go to v, it's like you just get ux squared plus uy squared. Okay. Then dx dy. Okay, so so that's clearly non-negative, right? So it can easily be convinced that this is greater than 0. Well, greater than equal to 0. Okay. So the question is whether or not it's 0 for anything which is non-zero. So the question is whether this is equal to 0 for a non-zero u. Okay. All right. So if the integral is 0, that implies that ux is equals to uy is equal to 0. Ux equals to uy is equal to 0. So u is sort of simultaneously a function of x alone and y alone. Which means it's constant. On the domain. Okay. But u equals to 0 on the boundary, which implies that u is equal to 0 in omega. Okay, so u actually has to be what we're trying to show is that if this thing vanishes, right, and so that means that point-wise ux and uy have to vanish, but if ux and uy vanishes, that point-wise that means that u is a constant function, but because u is also, it's like satisfies the boundary condition that vanishes is like on the boundary, right, that has to mean that u is actually identically 0 in the entire domain, which means that u is the 0 function. And so, so this equality, this inequality, it's like, so is only it's only, well, so this integral is only 0, right, if u is equal to 0, and otherwise it's a strict inequality, which shows that negative nabla squared is positive definite. Okay. All right. So let's just sort of note that, right, that nabla squared uv is equal to u nabla squared v. This is the symmetry property, and that if u is not 0, right, that nabla squared u is strictly greater than 0. Okay, so minus. All right. Okay, so now we're ready to to sort of analyze this Rayleigh-Ritz type method, okay, and see what happens. Okay. So because negative nabla squared is symmetric and positive definite, I can essentially introduce a new inner product involving that, right? Okay, so this is analogous to what happens where you replace, say, the dot product. So this is analogous to saying that instead of taking an inner product between vectors by U transpose V, right, I have another inner product, which is U transpose MV, where M is symmetric. It's a symmetric positive definite matrix, right? Okay, so that's basically the analog. So we want to do something similar. So I'm going to introduce a new inner product, which I denote by square brackets. So maybe I should do square brackets here, right? Sometimes that's bad notation because if you come from, you know some group theory, it's like, or if you know you work in quantum mechanics, then you know that that's the commutator, right? But anyway, it's like that's the notation which the book uses, so I will go ahead and use that. So this square bracket is going to be a new inner product, which is defined. It's like terms of this sort of negative of the Laplacian, right? Okay, so this is defined to be negative nabla squared uv and then inner product, right? So this is the integral of ux vx plus uy vy dx dy. Okay, and that was what we showed. It's like earlier, if you recall, when we proved that nabla squared is symmetric. Okay, so with this new inner product, you have a new norm as well, right? This also induces a new norm in the space V, right? So the norm of U is just the inner product of U itself. It's like the square root of that. Okay, all right. So anyway, so this introduces a new inner product and a new norm, right? And as you might expect, it's like what you might want to do is to frame the minimization problem in the context of this new norm, okay? And in particular, it's like, you know that in a sort of normed space, right, which comes from an inner product space, it's like you can, you can find this best approximation. It's like by orthogonal projection, okay? So, so the remark is that on an inner product space, right, best approximation with respect to the induced norm, right, can be obtained by orthogonal projection, right? Okay. All right. So you want this linear combination, right, to approximate the solution in the norm given by this inner product space. Okay, so we can write down the orthogonality condition, which comes from orthogonal projection. Right, which is that U, which is the exact solution, formally speaking, minus this linear combination should be perpendicular to each of the u's, right? Okay. So what that allows me to do then is the following. So this leads to the following. That the sum of j equals 1 to n of cj, uj, interproducted with ui, right, is equal to u comma ui. Okay. All right. So the fact that this is perpendicular basically means that you have equality in the space which is spanned by the ui's. So that's basically what's happening, right? So these two things, well, this is, let me rephrase that. This is equal to 0 in the ui directions, okay? So that's basically this equation here, okay? And then now I'm going to rewrite this in terms of the original inner product, right? But with the negative sort of nabla squared operator expressed in it. So this is equal to ui, right? Is equal to minus nabla squared ui, right? But the u satisfies an equation, so this is equal to negative f ui. And then, so I can put this back here, right? So this implies that negative, the sum from j equals 1 to n of cj, uj, ui, right, is equal to minus f paired with ui, right? But here it's like you have to be careful that you're using two different sort of inner products here. So this is the original L2 inner product, right? And then this is the L2 inner product, but where you have the operator negative nabla squared, it's like acting on this, okay? All right. So, all right, so you just have to remember that uv is equal to the integral of uv dx dy, and that this uv is equal to negative nabla squared u paired with v dx dy. Okay, but anyhow, so that's what you get. Okay, and so the important thing to realize, of course, is that we only use the u, right? We never actually end up using the unknown u. It's like in this defining equations, because I was able to replace u through the choice of this inner product, right, to have u acted upon by negative nabla squared, right? But because it's like u satisfies the differential equation, I replaced it with negative f instead, right? So, so now you're in a good situation. Again, this equation involves just the shape functions which you have chosen. The f, it's like, which is the source term, it's like in the equation which is given to you. And then it's like you have to compute these inner products. It's like, but at least in principle, this is a perfectly computable system. Yeah. So with that, it's like I'm going to stop here, and then we'll talk a little bit more about finite element methods in a little bit.